Hi, welcome to our talk about expanding programming language support in JupyterLite. So let's start right away. So first, let's have a quick introduction to Emscripten-forge. What is this? So it's a combination of the words Emscripten and conda-based. So let's first explain what Emscripten is. So Emscripten is this compiler toolchain which you can use to compile C, C++, and Fortran to WebAssembly. It's based on LLVM and Clang, and in a nutshell, it allows you to run pre-existing code bases in the browser or in Node.js, but we are mostly interested in running this in the browser. What are the use cases? Obviously, if you compile stuff, the first thing you need to compile is Doom and run it in the browser. But there's also more useful stuff for some people, like running Python in the browser. PyData was the first people who are doing that. Or you can even go even crazier. So you can compile Clang itself for the browser and run a compiler in the browser, or run a complete OS emulation in the browser. So you can run Linux inside a browser, and inside that browser running in Linux, you can compile Clang and run that. So you can go quite deep. Then what is conda-based? So conda-based is essentially just a distribution of conda packages. For those who don't know conda, it's like pip, but in good. It's community driven. That means the packages are provided essentially by you. You can make pull requests to some repository, and then the packages will be built in some CI. It's more or less language agnostic. That's a difference to pip, for instance. Pip is mostly for Python stuff. Conda, well, it's also mostly for Python stuff, but also for C++, R, and other packages. So it's multi-platform. So you can run, you can use conda packages on Linux, Mac OS, Windows, but WebAssembly is missing. And this is essentially where we step in with Emscripten-forge. So again, it's a distribution for conda packages, but it's specifically for WASM. So to be precise, it's for Emscripten WASM32. So in that sense, WASM is kind of the hardware you can think of, and Emscripten is like the operating system. Emscripten-forge is a bit like a poor man's conda-based, but it's also community-driven. You can make pull requests to our GitHub repository, and we will build the recipes. And it enables you to run C, C++, Fortran, Python, R, Lua, and many more, Octave, for instance, in the browser. But also in JupyterLite. This is what we are mostly interested in QuantStack, to run these languages in JupyterLite. So the kernels are the most important part if you run stuff in Jupyter. So let's have a quick look about the architecture and what the kernels are. So I hope this is not too small, but vanilla Jupyter, so the ordinary Jupyter architecture can be roughly described with these three boxes. So you have a kernel. The kernel is the piece of code or the entity which runs your code. So you have a kernel for Python, you have a kernel for C++, kernel for Lua. And they are connected, they run in their own dedicated process. And they are connected to a server, which is, again, a different process, and they communicate over sockets via 0MQ. And then this server is connected to a front end with WebSockets. Well, the front end is essentially just your browser. So this is the ordinary Jupyter like we know it and we like it. JupyterLite looks quite similar. So we, again, have these three boxes, but this time everything runs in your browser, right? So we again have a kernel. This time the kernel runs in a web worker. This is kind of like a process which runs inside the browser. Then we still connected to the server, which is again running in the browser, but this time we just communicate via JavaScript post messages to communicate from the web worker to the server. And then the server and the front end, they're just in the same JavaScript code environment, so to say, so they can just communicate with ordinary function calls. So, and if you compare those two, you see the number of boxes is more or less the same. So Jupyter and JupyterLite behave relatively similar. So the most important part of these three boxes is the kernel. The kernel is responsible for executing your code. So you can think of, you pass a string with what you want to execute, like print hello world. This is sent to the kernel, and then the kernel does its job. There are, of course, multiple kernels for multiple languages. And in principle, they can be implemented in any language. But we at Quantstack, we have a nifty library called xeus. That's a C++ library. And so if you write multiple kernels, there's a lot of boilerplate code or repetitive tasks. And this xeus library just gives you the abstraction to focus on the real things, or the most important things, executing your code. It handles the nitty-gritty details of the Jupyter protocol and makes life easier. And based on that library, one cool thing is the kernels you implement with xeus, they run in Jupyter and JupyterLite. So let me quickly give a tiny overview of the xeus-based kernels, and all of them run in the browser. So xeus-Python is the most important one. I think most people are using Python kernels with Jupyter, but there are many more. Some of them are just low-hanging fruits. Lua is easy to compile, SQLite also. Some external contributor gave us an OCaml kernel. JavaScript, also easy because you have it in the browser, right? But there's more advanced stuff like an R kernel. We will talk about this later. Isabel will talk about this in detail. And also xeus-Octave. For those who like MATLAB, there's also like an open source version, xeus-Octave. And xeus-CPP. xeus-CPP is such a big topic that there will be a dedicated talk, I think, tomorrow by Anutosh, who's sitting here in the audience. And now we will hear about how what are the challenges to pack these things that they run in the browser. And for that, I will give the microphone to Isabel.
Thank you, Thorsten. So now I'll talk about packaging R for WebAssembly. So this isn't anything new. It has been done before by WebR. And the WebR project also used Emscripten, and then they tried with a few different Fortran compilers to compile the Fortran bits of the R source code. But eventually they settled down with LVM Flang. And so to start off with, we needed to package all the core dependencies of R, of course. So luckily, most of them are written in C, so that was easy to do with just Emscripten. So we packaged all of these except for libcurl, but we also needed a way to compile Fortran code to WebAssembly so that we could have a BLAST-LAPACK implementation, which is required for the R source code. And just like the WebR project, we also, after trying a few Fortran compilers, we settled for LVM Flang. It has a modern LVM integration, and it is a very active project, so there's a lot of contributors to that project. So we thought it was a good option for our endeavors. And luckily, George Stagg, the developer of the WebR project, wrote a very detailed article about how to patch LVM Flang so that we could output WebAssembly objects. So we took his ideas and we created patches with the help of Serge Galton to apply to LVM Flang. And most of these patches have been already upstream, so now they're already part of the LVM project. And then we just need 3 additional patches to be able to output WebAssembly. And so then we had to package this patch version of Flang. So we maintain a recipe on the Flang feedstock in conda-based. We have it under the Emscripten branch. So if you would like to try it, you can install it with Micromamba or Mamba or whatever you use. So now we need to modify our toolchain a little bit. We have Emscripten to compile C and C++ code, and then Flang to compile Fortran code, and then we use Emscripten again to link everything together, and that gives us WebAssembly. So now going back to R, so cross-compilation of R is not enabled by default, so we had to take a bootstrap approach. So we had to do it in 2 phases. In the first phase, we had to build a minimal version of R so that we could generate some of the tools we need to generate more files in the build process. So these are the R and R script executables. And then in the second phase, this is when we actually cross-compile to WebAssembly using Emscripten in the patch flang package. And of course, we also needed to do a few more modifications to the R source code. We needed to disable the libcurl dependency, so this meant disabling the internet package in R. And we also changed the default graphics to Cairo instead of X11, and some other configurations such that we could set the correct compiler and linker flags to compile everything. So now we can finally package RBase. So this is a recipe. It's just a simple YAML file. So this contains all of the patches that I just mentioned. And then we have a build script that performs the phase 1 and phase 2 that I mentioned as well. And now that we are RBase, we want to expand the R ecosystem because we want to be able to use more packages. So luckily, all of the pure R packages that already exist in conda-based and are labeled as Norwich packages, we can just use those instantly because they simply work. And for those packages that require compilation, we have added some recipes to Emscripten-forge. But building R packages is very straightforward. You just need a single line to compile the package. And then we need this cross-R based package to handle all of the database files for each of the R packages. So before we can jump into JupyterLite, of course, we need a xeus kernel. So we already had xeus-R, which was written by Romain Francois. And that was already working well in JupyterLab. We just needed to make some small modifications so that we could compile it with Emscripten. And then we created a recipe and added it to Emscripten-forge. So a small demo. So this is JupyterLite, xeus-Lite running in the browser. And as you can see, the platform is WASM32. Before I mentioned that we had to disable the internet package, but we can still install other R packages with Magix. But, well, this one's already installed. And now you can see it working. Thanks. So now I'll talk about Octave. Just a brief introduction of Octave. So this is a very mathematics-oriented programming language. For those of you who are familiar with MATLAB, this will probably the syntax will probably look identical. But the difference with MATLAB is that Octave is free and open source. So just like R, for cross-compiling Octave, we needed to make a few modifications. So we had to disable all of the GUI functionality, and we also had to package all of the dependencies. But we already have a C, C++, and Fortran compiler toolchain, so that simplified things a bit. However, Fortran gave us a new challenge, and that was with Fortran common blocks, which LLVM could not handle. So we needed to create a new patch for LLVM. So we had to repackage LLVM with this patch, and we're hoping this is a temporary solution because Surge is opening a better version of this patch so that this can be contributed to the LLVM project. And then there will be support for common Fortran blocks. So then we needed another kernel, so xeus-Octave, which we already had a kernel that was working in JupyterLab. And just like xeus-R, we made some modifications. We created a new recipe that we added to Emscripten. And now for a small demo, well, I already had this running, but as you can see, you can make some nice plots. And everything is running in your browser. So for future plans, we want to have more Octave packages. That way we can extend the functionality of xeus-Octaves. So we want to add pure Octave packages to conda-based, but we also want to add other packages to Emscripten-forge for those that require compilation. And now I'll hand it over to Ian for JupyterLite.
Thanks, Isabel. So another use of Emscripten-forge packages is in the JupyterLite terminal. Now, if you've used JupyterLab, there's a terminal that sits in the front end that connects to a real shell, such as Bash, running on the server. In JupyterLite, we have an equivalent, but everything runs in the browser as normal. So we have a shell emulator, shell-ish, Bash-like shell, running in the browser. The commands that are run are the same commands you would run on any POSIX system, compiled to WebAssembly. Plus there's some TypeScript code that sort of combines it all together. There are actually two projects related to the JupyterLite terminal. First is called Cockle, which is the name of a type of shell. That's like a standalone implementation which allows us to have fast iteration of the WebAssembly commands and all the glue code that comes together. The second project is the terminal extension itself, so a JupyterLite extension that replaces the JupyterLab terminal extension, and that basically plugs Cockle into JupyterLite and does all of the boilerplate code required so we can have a shared file system between the two. So let's risk having a demo. Yeah, if you, thank you. Two hands and mouth at the same time. Right, so tab will give me a list of the commands available. So we have some fairly standard POSIX commands and a few sort of slightly interesting ones. Let's show sharing the file system. So let's say echo hello, I can't spell, to a dot, and of course I'm using tab completion, but you can't tell. So if I now cat a dot text, sure enough we've got some contents. It's over here. Let's double click on that, open it, and then I will type, sorry, goodbye. Save that, cat again, and sure enough, the two are basically the same file system, or it's pretending to be so. There are some slightly more exciting commands, so vim, if that floats your boat. So let's look at editor vim, so it works. It can take a few seconds to download the first time. Thank you. Thank you. And so we can add, I don't know, let's add some dull, pointless code just to show it working. You know, C equals A plus B. Obviously, this is all colored nicely. So this is like an example of full screen command that allows you to have input whilst the command is running, which is a much more complicated beast than like an ls or whatever. If I can remember the keystrokes to save and close, I can, and let's just check that. Yeah, sure enough. And finally, for those who don't know about :WQ, we can nano. We've also got nano. Oh, I won't swear. Yes, so we have another text editor, much smaller download. Or then I have to remember Control-X. Phew, got it. Okay. What else? Oh yes, let's show you uname -a. Ooh. There we go. So this gives us information about the system we're running on. It proves that we're running on an Emscripten system, so it's compiled using Emscripten. Final command to show you, there's a specific command to Cockle called Cockle config, subcommand package. This lists the WebAssembly packages from Emscripten-forge that are currently installed within this environment. So names on the left you will recognize, nano, vim. These are all hosted on prefix.dev, like all of the Emscripten-forge packages. Thank you, prefix.dev, for that. Shift onwards. This was just to allow me to check that I've said everything important, and I believe I have. One example of the recipe, for in this case for Vim, that works on Emscripten-forge, so two files, a recipe YAML and a build script. The recipe YAML, the important thing here is the code comes from Vim, so this is the original Vim source code, which was what started being written, I don't know, 40, 50 years ago, still compiles on a modern file system. What's with a modern compiler? Sorry. There's always some patching to be done, and in this case there is just one important dependency, ncurses, so it's a lot easier actually than Isabel's examples of all the R packages that depended on lots of different packages. And build script is quite long, but in reality it's C source code. It ends up being a traditional configure, make, and then a whole bunch of flags to get things to work, which are fairly common across the different commands. Final item. So when we first introduced the terminal at this venue a year ago, everybody was asking about, can we have command line git, please? Well, we sort of can. So that's a yes, but not quite today. But anyway, so we are working on a git2cpp, which is a C++ wrapper of libgit2. libgit2, C library that provides all Git functionality, as library calls, bulletproof, used by loads of people all over the world. It doesn't have full command line support, so we're doing relatively simple C++ wrapper for that. So we are starting from the ground up, adding functions one at a time, but it's relatively simple to do. And of course, there have to be some patches to deal with. For example, accessing GitHub remotely is not trivial. So today, I have it working on Cockle, but not the JupyterLite terminal. So there's a screenshot on the right of it working in Cockle. The JupyterLite terminal, the PR was merged last week. So the next release of JupyterLite and the next release of the JupyterLite terminal, so in the next 4 weeks, I'm guessing, this will also work in the terminal. The flow we've got on the right is all you can do, so don't try and do anything other than this. But we've got an example of, if I can highlight, so there's, oh, I can't, can I? So there's a Git clone of a remote repo. We've got adding a file, committing, log. So we've got some basic workflow functioning. We will be adding more and more functions, subcommands, one at a time over the coming few months. That brings us to the end. We have a QR code for you to look at our presentation. Of course, that has links to all of the JupyterLite deployments that we've been using for the demo. Thank you very much.
We have some time for questions.
Right, thanks, great presentation. We have in SciPy and other projects, like we're getting, support for both JupyterLite and PyData. It seems you have solved one of the hardest problems, which is dealing with Fortran. So looks great. So one part of my question is, can PyData use the same solution? Second part of my question is, what's the next hardest problem for making large packages, complex packages work?
Yeah, so the question was essentially if PyData could also use our approaches to compile Fortran code, and I think so, yes. So before that, we used PyData's approach and took a lot of inspiration from them, or copy-pasted. So I think now we can return the favor, and PyData could do that. So for everyone, before we had the Flung compiler, the way to compile Fortran code was you use F2C, which translates Fortran code to C code, and then you compiled the C code, and it was a huge hack. So we're kind of exciting. Then the second question was, what's the next big goal, right? Or so what's the next hardest problem? There are a few problems under the hood with respect to DLL loading. At the moment, when you start a Jupyter kernel and you have a lot, something like SciPy has a lot of SO files. And at the moment, before starting, you need to do like some magic dance with all of these SO files, and this takes a lot of time. Recently, Emscripten-forge landed, so a new major version of this compiler, and this added a few capabilities which allows us to not do this dance in beforehand. So you would only pay the price of doing the stuff with a shared library when you really import it. But there's a big caveat. At the moment, we are still on the 3.17 something branch, and one bad thing about Emscripten, the compiler, is it does not give you RB compatibility guarantees. So when we move to a new compiler, we have to recompile the world, which is a bit painful, but yeah, we're in the process. So hopefully soonish, I won't give any dates or timelines, we switch to Emscripten-forge completely. And then this long time to loading things will hopefully disappear. Yeah, I hope this answered the question.
Yes, thanks for the impressive talk. Could you expand a little bit more on the issue you had with libcurl? Because it looks like it's used mostly everywhere, but you had to discard its use in R, for instance. So could you explain us why is it so painful for you?
Yeah, so WebAssembly is a sandboxed environment. This means it just does not allow you to do certain things. Usually system calls are problematic. So anything which needs sockets or stuff like that is problematic. And WebAssembly in itself has not even a clock, no download capabilities whatsoever. Now, when you connect WebAssembly to JavaScript, it's not really a sandbox anymore because JavaScript can reach the world. But this does not give you stuff like sockets and so on. So what people typically do is you can download stuff with JavaScript. So what you do is you modify the fetch RP somehow and just dress it up a bit that it looks like curl. So on the Python side, all the like default packages to download stuff, requests and others, they just work, but there is some patching involved that it's just not using curl. Also for R, we recently added download capabilities. In R, there's a function called download, essentially, and you can pass it a string method equal to curl, and we just silently not use curl and download via JavaScript. So at the end of the day, it's just some manual work you have to do and modify the patches, do some monkey patching, and then you can have something which looks like curl and behaves like curl. But curl itself will probably not be in WebAssembly soon.
There's some time for last question. So let's say I'm a scientist, I want to publish a package on Emscripten-forge.
Yeah.
Can you explain the process?
Yeah, so first, if your package does not have any compiled code, then it's essentially for free. So if it's a no-arch package, it's already on conda-based, you can just consume it. So only if it needs compiled code, you need to put it on Emscripten-forge. And so usually you need a recipe, that's a YAML file, and what you do is you list your dependencies. All of the dependencies need to be either no-arch, so they are available from conda-based, or you need to add your dependencies. Sometimes this can get quite nasty because your dependencies have dependencies and so on. But let's say you don't have any dependencies and it's just some C code, then you just write make install and hopefully it works. Usually life is not that good to us, so often there are tiny details you have to, some tiny patches you have to apply. But if it's a good willing package, it will just work. And the procedure is you create a pull request with your recipe and your build script. And then it's built on our CI. And if everything works, the light are green of the CI and we merge it. Otherwise, yeah, one needs to iterate and hopefully you get help from us if it's not working right away.
Okay, let's thank Isabelle, Jan, and Torsten once again.